Okay, ladies and gentlemen, we'll get underway again. And this session will discuss one of the key focus areas of the World Energy Outlook 2014, which is the focus on nuclear energy. And to chair this session, we have Professor Andrew Stutchbury, who is the head of the Department of Nuclear Physics here at ANU. And Andrew and his department are the custodians of the Heavy Ion Accelerator Facility, which is the largest nuclear science facility in the country, and indeed a major national facility. And Andrew and his department have a significant amount of expertise in the area of nuclear science, and indeed on the side of nuclear energy to some degree as well. So I'll just hand over now to Andrew.
Thanks, Ken. Let me just clarify a little bit. Our department is custodian of the Heavy Ion Accelerator Facility, and most of our research is heavy ion accelerator-based research. It's not directly related to nuclear energy unless you count the accelerator mass spectrometry we do on trace amounts of uranium and plutonium and neptunium isotopes that we do to monitor discharges from nuclear processing plants. However, what is related to nuclear energy is that we run a Master of Nuclear Science program. It's a kind of a sister program to the Master of Energy Change program. And I've been convening this program since about 2007. We set the program up to teach nuclear science to a broad audience. The idea was to inform discussion on nuclear energy without taking a particular position. And we have done that. The outcome after these years is that the majority of the students in the course, in fact, have come from government departments where their work is concerned with nuclear safeguards and or nuclear security. So the discussion in this session is on the World Energy Outlook for nuclear power, and we're here to discuss the global outlook in a world of increasing energy demand and in the face of climate change. We have 4 panel members who will talk on this topic. Broadly speaking, we have 2 physicists who hold leading positions in government agencies or organisations, and 2 environmental scientists. So I'll briefly introduce these people, and then we'll have a 10-minute presentation from each one in turn, just following the order that's on the printed program. So firstly, we have Dr. A.D. Paterson, who's CEO of ANSTO, the Australian Nuclear Science and Technology Organisation. And he came to ANSTO formerly holding the position of General Manager of Business Development and Operations at the Pebble Bed Modular Reactor Company in South Africa. So AD has expertise in nuclear technology for nuclear energy. The last speaker will be Steve Cowley, who's CEO of the United Kingdom Atomic Energy Authority. He's also director of the UK AEA Culham Centre for Fusion Energy. So I expect Steve will say a little bit about nuclear energy and about fusion as well. Then we have our 2 environmental scientists. We've got Barry Brook. Barry Brook is a Professor of Environmental Sustainability at the University of Tasmania. And until recently, he was the Sir Hubert Wilkins Chair of Climate Change in the School of Earth and Environmental Sciences at the University of Adelaide. Barry considers himself a Promethean environmentalist. I found this description. So he seeks effective techno-fixes to solve entrenched sustainability problems. And then last but not least, we have Professor Ian Lowe. Ian is an Emeritus Professor in the School of Science at Griffith University, and he's President of the Australian Conservation Foundation. His principal research interests are in policy decisions influencing the use of energy, science and technology, energy use in industrialised countries, large-scale environmental issues and sustainable development. And an interesting thing is that Barry and Ian have written a book together taking opposite sides in the nuclear debate. So without further ado, let me hand over to Adi to speak first on our topic of nuclear energy outlook.
Great. Thanks very much, Andrew. I'll just get teed up here. Well, good morning, everybody. It's great to be here as part of this meeting and an opportunity to talk about nuclear energy. That's the title of the entire session, so I thought might as well make it the title of my talk as well. I'm formally a government official, so I can't take policy positions because I'm more advisory. So you might find me not taking any particular policy positions in relation to Australia, but I do have a mandate to talk more broadly about issues related to nuclear energy. And if we can have a good timekeeper as well, because I might get overexcited. So nuclear reasons to stay engaged in the nuclear energy discussion in Australia. Well, I think we'll hear the report this afternoon. Global energy demand is undergoing asymmetrical growth. You've got it flatlining in the OECD, growing dramatically in other parts of the world. We're in the other part of the world where it's growing dramatically and where energy utilization is going to really be driven by cost. For many people, an escape from energy poverty as well, which is an important dimension of this debate. Nuclear will play a role. Energy density of nuclear systems, the need for some level of fuel security, carbon dioxide is absolutely critical in that debate as well. But there's some other factors in the region which include things like population density that take dilute sources much more quickly out of the picture than in large desert areas where one can expect to put up dilute sources of various sorts. Short to medium term options for many parts of the region will include small modular reactors, typically reactors that have got per unit about 250 megawatts electrical at the top end, but as low as 40 or 30 at the bottom end. And then medium to long-term generation 4 type reactors, reactors which we don't have well established around the world, but which are seeking to overcome some of the challenges of the generation 3 and 3 plus type of reactors. It is my view that if the energy poor nations of the world are to benefit from nuclear energy, that we will have to move beyond the sovereign state model of people adopting nuclear to a more global model. We used to have sovereign state models of how you flew aircraft around. Every country that wanted to fly aircraft had its own aircraft manufacturing capability. We've moved to a global model. I think over the period of the next 40 to 50 years, we will see more and more countries come to a common mind and adopt a coherent approach to a global model for nuclear power rollout. Australia needs to take a strategic view of the fuel cycle. We're certainly at the front end of the fuel cycle with respect to uranium. Some of those of you who follow the various bits of nuclear news will have noted that Kazakhstan and China signed a cooperation agreement just this week saying that they're going to work together at the front end of the fuel cycle as well. And I think an underlying overall question is, are we going to be part of our region or not? So this is a scale that we use to look at the extent to which countries are involved in nuclear power. This particular typology, which was developed by some colleagues at ANSTO, has green as adopted, red is excluded. The nomenclature is sort of chosen to show a map of Asia, which is our region. And it's important to note now that you can get everywhere from Turkey right across the world, jump over North Korea all the way to Japan, and you can get right across the diagram now. There are various other ways to get across the diagram in terms of where countries are and their level of commitment to nuclear. These are the specific commitments that we have in place at the moment. Japan is a bit of a wild card. We're not quite sure where that is going to land. But a country like Turkey has got a major nuclear program which is being developed initially by the Russians. Saudi Arabia is talking about a significant number of reactors. I spent some time in Jordan recently and had discussions with them at a senior level about their program. And last week, or the week before last, we had the Forum for Nuclear Cooperation in Asia. The ministerial meeting took place in Sydney. And so we caught up with most of the other countries on this diagram in terms of where they are with their programs. So whatever happens in Australia, we certainly are going to be in a nuclear region, and a region which will be dominated by the adoption of nuclear technology increasingly over the next decades. Why is this important? Well, this is from the ExxonMobil scenarios from 2013. You can see that if you're going to mitigate the fossil carbon-based sources, you're going to need renewables. Most people who are thinking about 80%, and I certainly live and dream the 80% mitigation of carbon, I don't think there's a rational pathway to 80% mitigation of carbon without having nuclear as part of the mix. I think it's impossible to achieve. Most of the modelling that I've seen ex the UK suggests at about 50% it gets really, really difficult if you don't have nuclear as part of the mix. This is our region, the blue part down at the bottom. Let's see if I can get a pointer on there. And you could take the country of Bangladesh, for example. Bangladesh, 161 million people. They use 1/40th of the energy that the average Aussie uses on a daily basis. So you take that country with 161 million people and you say, how do they climb out of energy poverty? And the answer is they have no room because of the way that population has used up all of the areas that they have to have any dilute sources. So like South Korea, they're likely to adopt high density sources and adopt them in a way that allows them to build their nations. So the blue there basically means that Bangladesh uses about 1/10 of the energy that a Canada would use, for example, per capita. The circles tell you the population of those countries. Now, I've found out that people can't actually translate circles into population, but if you think about Bangladesh, it doesn't look that much bigger than Australia, which is that yellow dot next to China, but it is actually many, many times bigger population, 161 million people. So if you think about this region, and you think about energy poverty, and you think about the escape from energy poverty, and you think how that can be done in an efficient way, you certainly want to have an electricity that you've got in that. And that means that you're going to have reliable baseload sources. Some people have declared baseload over. I think it's way too early to do that. So just if we look at China, for example, which has got a major build program at the moment, if China completes the build that it's currently got on by 2020, it will essentially only have as much nuclear as Australia's got energy. Electricity-based energy at the moment. So China, although it's building a very big program of nuclear reactors at the moment, it's having almost no impact on their carbon footprint. And remember that their nuclear capabilities will be significantly bigger than their renewable capabilities. Because that's the real China that we're looking at in terms of the capacity that has to be in there. Currently, this year, 1,146 gigawatts electrical, and still relatively energy poor in comparison to the United States and other OECD countries. So I think the underestimate for me in many of the scenarios that I look at is the aspirational needs of people to escape from poverty, to get on a developmental pathway that is meaningful to them and allows them to fully participate in the global economy. When we start the debate there, you have to give people choices where they can build big plants that will sustain large numbers of people as they undergo the normal developmental phases of industrial growth. So Australia, when I arrived here about 6 years ago, was, I think, number 3 at the top of this diagram. I think this 2013 figure is no longer accurate. What I don't understand from a policy perspective, and I haven't seen anybody write this up, is how do you get from the top of the diagram to the bottom of the diagram by having aging fossil plants that you're not replacing? It's a remarkable achievement, which we are experiencing in our pockets every day. And unless we understand the economics of how this mix is going to develop, I'm reckoning in 4 years' time we'll be north of Denmark. And Denmark needs Norway to bail out their renewables with decent hydropower. So just a couple of words about reactors. This is the current nuclear power world. Up the side we have regulator capacity. The regulator is the slow step. Sometimes it's the banks, but it's the banks or the regulator. And the current nuclear power around the world is large. It's been slow to build. It's expensive up front. And it's really not been that evolutionary in terms of design until we got the Generation 3 plus plants now. The current small modular reactors are really at the early stage. A few are being built around the world. A couple of exciting projects in China, including a pebble bed modular reactor there. But in order for this to become sustainable and to roll out fleets of small modular reactors, because these are factory built, you want to build them in factories, you want to transport them easily, you want to put them in holes in the ground, they plug and play and they're all meant to work. We haven't seen that era yet, but that is what is being talked about for small modular reactors. And many of the countries that become involved will not want to maintain a fuel cycle for themselves. And so we have the buy, burn, return fuel cycle. Even more challenging are the Generation 4 reactors. And one of the very difficult things to do is to follow the yellow arrow, which is to be a small country that doesn't have a nuclear tradition, a new entrant in other words, and to try to get a Gen 4 design that works and gets you up into that design evolution top corner, the green zone. So I believe what we're going to see is the established players gradually globalize this industry, set standards for regulation, set standards for safety, set standards for fuel, set a whole lot of standards, and that global supply chain will then be designed to move into this area where the current nuclear power fleet is sitting. And as that's retired, the small modular reactors are going to come in. So when you get your hands on this talk, this is just a sort of a typology that is meant to help you in making decisions about where you want to be and how you want to do it. It seems unfortunate to me that we've just restarted part of the debate in Australia, and there have been statements made, certainly over the last week. I haven't heard the word social license yet, but it seems to me crucial that if we've learned anything in Australia about nuclear, we've learned about the need to have an informed public that is engaged early and where independent information builds trust. Familiarity and understanding correlates with public approval. The UK is the first nation on earth to break the gender gap in understanding of nuclear, and we've seen over the last few years women and men in the UK start to agree about nuclear. In most of the rest of the world, there is a significant 15 to 20% gender gap in debates about nuclear. You can't have that and have a modern consensus-based approach to how we utilize our resources. So there are reasons to stay involved. There's global energy demand, there's asymmetrical growth in our region. That's an opportunity for us. Nuclear will be part of that. It's impossible to get to 80% in meaningful ways for energy-poor countries without using nuclear as part of that mix. In the short to medium term, nuclear options for many countries will be small modular reactors if we can get a genuine sovereign, post-sovereign approach. And in the medium to long term, Generation 4 reactors are going to become crucial. So I'm arguing that we should, over time, in a rational world, seeking energy solutions, particularly for the poor and the economically excluded, move beyond a model that's based on sovereignty towards a global model. We all need to maintain a strategic view of the fuel cycle and make sure that it's operated safely, securely, and with good safeguards. And the challenge for Australia is in this discussion, are we going to be relevant in our region or not? This is the very beautiful Opal reactor, the only operating nuclear reactor in Australia. ANSTO tries to make sense of nuclear. Thank you.
I think we'll hold questions and discussion until the end of the panel presentations. So let's move to the next presenter, which is Professor Barry Brook.
So Adie's given an excellent introduction to the topic of nuclear energy and Australia's position in it, and he mentioned a number of times that he sees a long-term role for Generation 4 nuclear technology. And that's what I want to talk a little bit more about today in the short time I have to give this presentation. And I term it sustainable nuclear fission to separate it from nuclear fusion, which is another form of potentially sustainable nuclear energy that will be talked about by another panellist. And I consider it sustainable because of a number of attributes of that nuclear fuel cycle. Now, if we imagine what our future energy landscape is going to look like, a typical approach, one used by modellers such as those that do integrated assessments that build in models of the economy and energy growth, tend to start with some reference scenario and then consider how we may move from that business as usual reference scenario to some alternative, in this case ideally a low carbon alternative, one that meets particular carbon mitigation goals. And I and a few others tend to refer to this as the layer cake approach, because it essentially takes the whole cake and then slices up into different layers, all of which can contribute to that carbon mitigation. And that's a reasonable assumption to make, that we will have a mix of energy sources. That was something that AD emphasised and Stephen Chu emphasised in his talk, that we're not going to get there with any one particular energy source. And nuclear is in there as a wedge. So at the very least, I think you should accept that nuclear is going to be a wedge, and a wedge that fulfills certain roles that other energy sources can't. However, the history of energy in some countries suggests that it typically won't play out as a nice even layer cake. Some countries, such as France, for instance, when it moved away from about half fossil and half hydro, took a nuclear intensive approach. So in that case, the layer cake was mostly a soft filling in the middle of nuclear with a layer of other things around the outside. Other countries may take different routes, and that's fine. Australia may or may not take a route like this, but we know that this is a viable route. A country has done it. And we know from the past that countries have typically all taken a similar route, which is a nice fat layer of coal. And that's something that we definitely want to avoid in the future. This is the results of some work I did a few years ago that agrees very much with what the figure that was just presented by AD, about a 350% increase in demand. This was just me looking at the different low carbon energy sources, future demand, and not just at electricity, but also the replacement of transport energy, so replacement of oil with some combination of battery electric vehicles and synthetic fuels like hydrogen or hydrogen derivatives. The whole integrated energy system will require a massive expansion, even with continued pursuit of energy efficiency and conservation. There are so many roles that electricity and other new energy sources have to displace that we're going to need a lot more energy. And of course, in many countries that are energy poor, that growth is going to come just to catch up with where many of the OECD countries are. So in that scenario, for instance, I looked at, it wasn't a prediction, it was a scenario where I said, what if by 2060, so about 50 years in the future, we could eliminate our dependence on traditional fossil fuels? What might the mix look like? And in this case, the scenario had the largest amount of growth in terms of relative growth year in, year out assigned to wind and solar. So a 50-fold increase in wind and solar compared to our capacity today, and a smaller percentage increase in nuclear, 15-fold increase, and then some growth in hydro and biomass and potentially a wedge of fossil fuels with carbon capture and storage. So even taking the extremely optimistic line for renewables and saying a 50-fold increase, and a more conservative line for nuclear, given that it has a larger installed base of 15 times, we still end up with about half of that supply coming from nuclear in that case. Again, that's not a prediction, but that's saying even if you go full steam with renewables, you still need a lot more if you're going to get to those true zero carbon goals. And that's potentially a strong role for nuclear. It's that other 50% that Stephen Chu mentioned that becomes very difficult in any other way except something that is essentially a plug-and-play replacement for coal. Now, I suspect it could be much larger, it could be smaller, but it's going to be a significant wedge. Now in Australia right now, that green is all black and brown. It's all coal. So if we want to move away from that, we have a large challenge not only in growing renewables, but also in starting and in growing nuclear. But my vision for nuclear is not your grandmother's version of nuclear power. It's the next generation. It's unlocking all of the potential energy in uranium. As that comic illustrates, there's a lot of it in there. About 1 million times more energy than in a chemical reaction. If you can unlock it all, then you have a vast supply of low carbon energy. If you can't, then it's still an efficient form of energy, but not as great as it could be. So nuclear technologies continue to evolve over many decades. I'm talking about the next generation, which is not really an incremental evolution, it's a revolution in terms of how the systems operate in terms of safety and recycling of fuel and so on. Now, it's not just an idea. It is a reality. It has been practically demonstrated. The largest single energy in research and development investment in the United States in non-fossil fuel energy has gone into this technology, this integral fast reactor technology and related liquid metal fast reactors. And so it's actually a well-developed concept that most of the stages have been proven out and developed to a stage where it's a very reliable technology. The part of it which still requires the final scaling is the electro-refining of the spent fuel. But that's a really critical step that's now being worked on. It's been demonstrated at the laboratory scale, not at the commercial scale. But it's a key step in closing this fuel cycle. If you're interested in how that American technology was developed from about 1964 through to the end of the 20th century, then I would encourage you to read this book that was written a few years ago. It also tells a good narrative about American energy policy in general. It's called Plentiful Energy, and it was written by a couple of scientists and engineers who were involved in the development of this program. Fascinating read. But my vision of that type of nuclear technology is that we have a fuel cycle which doesn't just move through the chain once and then is left with the problem of what you do with spent fuel at the end. So that's the top sort of part of that slide. I'm not sure whether we can see that. No. It's the top part of that slide. Here we are. That's a traditional fuel cycle. You mine the uranium, you enrich it, you run it through a light water reactor, you generate lots of low carbon electricity, but then you have spent fuel that has to be stored for potentially hundreds of thousands of years in an isolated geological repository. The alternative is that you take that spent fuel that already exists and you manufacture it into fast reactor fuel, recycle it many times in a fuel recycling centre. What eventually comes out then is being stripped of all of the long-lived radioactive waste, and all it has is the short-lived fission products, which have a much shorter lifespan. So they still go into the repository or some other engineered facility, but not for 300,000 years, more like 300 years. So we move from this philosophical problem of how you manage waste for 100 times longer than modern civilization to one which is an engineering problem of how you manage it for a few centuries and potentially recover the valuable products. And the two really major advantages of this are, one is that you cut this radioactive lifespan by orders of magnitude. And the second is that you take what is currently a waste product, which is spent nuclear fuel from today's reactors, and you turn it into abundant low carbon energy. If you fully recycle that fuel, you get about 150 times more energy out of that fuel than you would otherwise get. So that means that you've got all of this abundant, already available, zero carbon fuel. And you've solved your long-lived nuclear waste problem. It's a very attractive proposition, and I think it's the type of new technology, the sort of breakthrough technology that we ought to be investing in, because it solves many entrenched sustainability problems and potentially provides a major solution to decarbonising our economy. My final slide, I just want to reinforce that energy density matters. So when we're all talking about nuclear energy here, we're talking about the most dense form of energy, the most concentrated form of energy that humankind has so far developed. If you were to imagine all of the energy you used in your entire lifespan, that's not only your electricity, but also the energy that goes into your transportation, your car, your flights, the energy that goes into producing your food, everything. Then in fact, in a fairly conservative assumption, you could say it could all be contained within a golf ball in the guy's hand of uranium for your entire lifespan. So your legacy of waste would be 300 years of a Coke can of waste. And just to put that in perspective, if you were to do it with natural gas, compressed natural gas, you would require around 58 natural gas tankers for each and every one of us in here. If you were to do it with coal, you would require the amount of coal equal to an elephant, and then you multiply that by 800 times, so 800 elephants, about 3,000 tonnes of coal for each and every one of us here, so that's a large amount of coal. And if you were to store it in currently commercialised nickel metal hydride batteries that are used in, say, a Prius car today, then you would require a battery the size of an elevator shaft, and an elevator shaft would be 13 times taller than the elevator shaft of the Burj Khalifa building, which is currently the tallest skyscraper. So a lot of materials go into that. So we can't avoid the fact that if you want to capture diffuse energy sources, then you need a large infrastructure to do it. If you want to capture dense energy sources, then potentially you have a much smaller footprint. So I'm not here to say that we shouldn't be pursuing solar and we shouldn't be pursuing wind energy, we shouldn't be pursuing an energy mix. But I think if we're really serious about mitigating carbon emissions, we ought to be seriously pursuing advanced nuclear technologies that solve a number of our entrenched energy problems and provide potentially a very bright future for humanity. Thank you.
Thanks, Barry. We'll move straight on to the next speaker, who is Professor Ian Lowe.
Thanks, Chairman. I agree with some of the things that Barry and Adi have said, and I disagree with others. I'm going to talk about the question of what future there is for nuclear energy, but I wanted to contextualise that by making some comments about the World Energy Outlook 2014 paper. I don't want to pour too much water on the pitch that our guest has to bat on this afternoon, but I did want to make a couple of qualifying comments about that because there are some things about that that do worry me. 40 years ago, Limits to Growth was published and said that if the growth trends in population, resource use, industrial production, agricultural output and pollution were all to continue, we would reach limits within 100 years, and the most likely result would be economic and ecological collapse in the middle decades of this century. Dr. Graham Turner of CSIRO has done a comparison of the standard run of the Limits to Growth model with 40 years of data, and we are right on track for that gloomy outcome. Now, of course, that may be a policy objective for this generation of leaders, but it's not one I think they would like to be remembered for. And just in case you think that it's only scientists and modellers who are saying that, the World Economic Forum, which is basically the big end of town at a global level, said at the end of their summit on the global agenda in 2008 that the recent crises of fuel, food and finance are the canaries in the mine, the early warning signals that our current economic system is simply not sustainable in the sense that you cannot have unlimited growth in resource use in a closed system. Why is that important? Well, the World Energy Outlook report basically promotes increasing energy use predominantly from fossil fuels. Its gloomy counsel is that we can only expect to improve efficiency by 15 or 20% over 25 years, and it's really a counsel of despair on climate. It says in quite sanguine tones that following what they see as the standard development model will commit us to warming average temperatures of 3.6 degrees plus or minus. And of course 3.6 degrees average means 5, 6 or 7 for somewhere inland like Canberra. And while Canberrans in winter might appreciate the idea of 6 or 7 degrees increase in average temperature, I doubt if they would in summer. Under their standard development model, emissions from power use are still getting worse in 2040. And if you integrate the carbon dioxide emissions from just the electrical sector from now to 2050, it's about 500 gigatons of carbon dioxide, which is about the total global budget if we want to avoid dangerous climate change without allowing for any other minor uses like transport. A more prudent view, I believe, would be to try and avoid dangerous climate change. And what the Australian Academy of Science says, if we want to do that, total global emissions need to peak by 2020 and then decline rapidly. I think efficiency is absolutely crucial to meeting that objective while meeting the legitimate material expectations of people, particularly the poorer parts of the world in this region. The report on resource efficiency and economic outlook for the Asia Pacific, published about 4 years ago, called for a new industrial revolution in which we meet people's legitimate material expectations using a quarter of the resources we now do. And I think if we're serious about meeting legitimate expectations within an acceptable carbon budget, we have to be much more aggressive about improving the efficiency of turning energy into services. As Amory Lovins famously said, people don't want energy, they want hot showers and cold beer. And the technological challenge is to provide services with much less energy. I believe the proposal to increase coal use to more than 6 billion tonnes a year is just taking an irresponsible risk. To be fair, it's not as bad as our government's so-called green paper, which probably should have been called a brown paper. I noticed this morning that the European NGOs, in a ranking of 58 countries, ranked Australia 57th for our effort on climate change, worse than Kazakhstan. The good news is we're still ahead of Saudi Arabia. The Energy Outlook paper has a guarded view of nuclear. It notes that nuclear has declined from 18% of world electricity to 11%, and their pro-nuclear case has it increasing to 12% by 2040, which would probably disappoint Adi and Barry. The low nuclear case, it's only meeting 7% of energy needs in 2040. But it notes two problems. If growth continues, in other words, if it expands to 12%, which would be about a 50% increase in current generating capacity, the spent fuel burden, unless the new technology that Barry advocates is implemented, will be about 750,000 tonnes by 2040. And in that period, about half of the currently existing reactors will need to be retired, and they estimate the decommissioning costs at more than 100 billion. So I think that even meeting that task is not a small challenge. Underlying a lot of the discussion about nuclear power is what's been called the deficit model. Those who advocate it implicitly say that we are wise technical experts who support nuclear energy. Those who oppose it are ignorant. If only the community were well educated, they would see reason and accept nuclear power, and we must therefore educate the community. I think there's some problems with that approach. The first is that not all technical experts support nuclear energy, and the second is that not all the technically ignorant oppose nuclear energy, as a couple of government ministers have recently demonstrated. In fact, there's no hard evidence of a correlation between technical education and support for or opposition to any particular technology, either solar or nuclear. I think we have to be aware of what's been called the May effect. Lord Robert May gave a paper to the UNESCO World Congress on Science in 1996, pointing out that the scepticism about advanced technologies, like integrated fast reactors and genetically modified food crops, is actually higher in countries that are well educated scientifically. And his explanation is that only the scientifically naive believe assurances that a technical advance will be an unmitigated good. And he said those who understand the technology appreciate that there is always a trade-off. There are always risks as well as benefits. And he said we shouldn't be surprised that a more educated community is more critical. So educating the community to understand nuclear power better might actually make them more hostile rather than more positive. And I'd remind you also that educate is one of those irregular constructions. I educate, you persuade, he brainwashes. That one person's education is another person's propaganda. What are the concerns? Well, I think the concerns of the community broadly are that nuclear power, for Australia anyway, is too expensive, too slow, makes too little difference, and there are the continuing problems of operating risk, management of waste, and ensuring that fissile material isn't misused. The Switkowski report was produced by, as John Clark put it, an independent group of people who want nuclear power by Tuesday. Whether that's accurate or not, they certainly couldn't be accused of being biased against nuclear power. And their conclusion is that nuclear in Australia would cost 20 to 50% more than alternatives. 15 years would be a realistic time to build one reactor. And a crash program of 25 reactors would not cut our greenhouse gas emissions, but only reduce the growth in our greenhouse gas emissions by 18%. And they said waste remains an issue. I think that suggests that the concerns are well grounded. And the AMP Capital Investors report said that until there is a proven solution for waste management, the industry is transferring the risks, cost and responsibility to future generations. That unless there is a program of waste management or waste use or reprocessing that the community accepts, it's unlikely to be accepted. In terms of the risk to communities, I suppose after well-publicised accidents, it's understandable that there are concerns. And the concerns, I think, revolve around the fact that we don't understand Earth systems well enough to be confident that anywhere is a secure site, proof against the worst that nature can throw at us. Just as a personal example, I was sitting in Coffee Culture in High Street, Christchurch, at lunchtime on February the 11th, 2011, having ordered a flat white and a toasted panini, blissfully unaware that where I was sitting was actually a dangerous place. It didn't look like this after the first tremor, after which I escaped. I was 200 yards away when the first aftershock reduced it to a pile of rubble. But the point is that Fukushima was overwhelmed by a tsunami that was much worse than predicted and much worse than the precautions that had been taken. And we need to be aware that we simply don't understand natural systems well enough to be completely confident. I think, as Fukushima reminded us, nuclear demands a strong and independent regulatory approach. And I noted this recent comment by President Xi Jinping, who was unashamedly bullish about nuclear power, and he said it has a bright future, but without proper safeguards, he said, such a bright future will be overshadowed by dark clouds or even ruined by resulting disasters. I think we should certainly be working on better technology if we envisage nuclear being part of the solution. It may be that we can get Generation 4 reactors or integral fast breeder reactors to work at a level that may attain community acceptance. Thorium may also be possible, and I'm sure we're going to be told that fusion is no longer 50 years away, but perhaps only 30 or 40. And of course, if fusion could be made to work, that removes almost all of the problems that are entailed with fission. Just a final obvious qualification, every country has a unique situation in terms of energy needs, resources, technical and regulatory capacity. No blanket assertion applies to all, but I think given that we have relatively large land areas and relatively small populations, Australia and New Zealand are especially well placed to use renewable energy technologies, which is why there's been such a rapid expansion despite governments being out to lunch on the issue. So finally, I think real community concerns will not be allayed by bald assertions, and we need to recognise that values are critical in assessing technologies, which is why there is no one answer which everyone will accept. I think it's clear that both cost curves and community attitudes are favouring renewables at the moment. And I think the question that has to be answered is, if renewables can meet our needs, why would we expand nuclear power? Thank you very much.
Thanks, Ian. So now we'll welcome Steve Cowley to make his presentation.
It's delightful to be here. Thank you very much. This is on, so I don't have to worry about it. I'm I'm not going to show any slides because tomorrow I'm going to give a scientific presentation of where we are on fusion. And what I'm going to talk about is part of the rest of my role somewhat in the UK and where fusion fits into that. In that I am responsible in some sense for some of the issues of what our nuclear future in the UK might be. I think this might be useful to an Australian audience, not perhaps as useful as what Australia should do, which I have no opinion on. I'm also not going to show any PowerPoint because I don't want this to be an official statement of what the British government thinks about the future. It's much more useful to you if I tell you what I think rather than I tell you what I'm allowed to say. We have a three-stage problem in the UK right now in energy. We have a problem that our ageing infrastructure in energy is well and truly ageing, and what used to be a 20% capacity margin on our grid, generating capacity margin of 20%, has shrunk to a 4% capacity margin, which means that one more reactor out of commission or one more power station, coal-fired power station that has a problem over this winter, and the Prime Minister will have to explain why there's a blackout. In the 1970s we had blackouts in England, but we didn't have to explain why, right? There was a union leader that we could point to and say, he's the problem. So that's a problem about the capacity. It's mostly about regulation and capacity margins and things like that. And what you'll see over the next few years is that the UK will up its levels of fossil fuel-fired power stations in order to make sure that we have enough capacity for demand. So that will take us through into the 2020s, and our goals of decarbonising the British energy generation over that time will not be met in the short term. Right? We started putting out goals around 2000, and we have the goal, like everybody else, that by 2050, 80% reduction in our CO2 output. All of that's on hold at the moment. It's partly on hold because we're late in delivering the 16 gigawatts of new nuclear power stations. Britain built nuclear power stations during the 50s, 60s, 70s, which were called Magnox power stations. These were CO2-cooled nuclear power stations. And then we produced a second generation, which were the advanced gas-cooled reactors, which are the ones that are largely operating now. And they're all due for retirement. And there'll be retirement up into the 2020s. They've all been extended in life. It's one of the great things about nuclear power stations is that actually they were largely conservatively designed, the ones that we did in Britain, and we've been able to extend their life, and that's sort of printing money to some extent. But they will come to an end shortly, and we're seeing cracks in steam generators and things like that. Not a danger of a nuclear accident, but something that you have to close down for. And this will mean that they may retire spontaneously in the next few years and put a big hole in the market, because a typical British day, you want 40 gigawatts of power. One station will produce 1 gigawatt. So it's quite a big perturbation to lose 1 or 2 to the system. So the second stage, I told you there were 3 stages that the UK energy system has to go through. The second stage it has to go through is a transitional stage to decarbonisation. And there are transitional technologies, and this is perhaps my message of this talk, is that at this point, nuclear is a transitional technology. It will allow us to decarbonise quite quickly in the next decades with existing technology without research. So if you look at the plan at the moment up to 2050, in 2011, the Department of Energy and Climate Change published its carbon plan. And these were 4 scenarios as to how you would decarbonise the British electricity generating system. And one of the assumptions, of course, is by 2050, the amount of electricity we use has gone up considerably because we will be driving electric cars and electricity will be providing more of the heating or heat pumps for homes and things like this. So we're talking of going out from a sort of 72 gigawatts of installed capacity up to 110, 120 gigawatts of installed capacity. So there were 4 plans. And those 4 plans, the least amount of nuclear was 16 gigawatts. And on one of the plans was 75 gigawatts of installed nuclear capacity. Huge, more than we saw the Chinese installed capacity. Because the 4 planks of decarbonising the British energy system were carbon capture and storage, wind, and nuclear. And those 4 plans had different mixes of those. And our government is pretending, and probably understanding that this is partly a pretense and partly true, is that the market will work out the exact balance of those 4 things. Sorry, I only gave you 3. The third one, of course, is reduced consumption. Right? You've got to, part of all of those plans is a reduced consumption and getting people to save energy more. We are having trouble delivering the first of the new nuclear power stations, Hinkley Point, which is down in Somerset. The difficulty is the unit size is quite large, and the unit investment is very large, and it's hard to raise that investment in the current climate. And one of the things that worries me tremendously is the government's been very happy to spend 10 years trying to get together the regulatory environment and the financing for a power station, and would like to see it built in 4. As an engineer and a physicist, I feel that they're putting the onus on us as opposed to the onus on making political decisions quickly and surely. Because if we are to get even 16 gigawatts of new installed nuclear capacity, we have to get building quite quickly. We cannot build them all at once. We have to build them sequentially because we don't have the building capacity in the UK to do that. But the third stage of building a sustainable energy system that's decarbonised will see carbon capture and storage and nuclear, once through nuclear, have to phase out. We cannot go on doing the kind of nuclear we do at the moment, which is the once through cycle with no reprocessing, no breeding. We cannot do that for more than a century, and probably not more than, say, 70 years. So this next generation of nuclear power stations will be the ones of this kind. And beyond that, the capacity to store the waste, the price of uranium, will drive changes in the nuclear systems that we have to use, and we will have to go to the Generation 4 systems, or what are the options? So we're now into what stage 3 might be for the UK. Stage 3 for the UK will have a limited amount of carbon capture and storage, probably for about a century. But beyond that, that will have to phase out. On nuclear, there are 2 options. One is the advanced nuclear systems that Barry was talking about, the Generation 4 systems, where we do reprocessing of fuel, we burn the waste, so we don't have to store it for long periods of time, and we go to the what are called fast neutron systems. And the second nuclear option is to go to fusion. It's not as far away as you might think. Okay, so it might be 30 years. You know, you got in there before me, because whenever I talk about fusion, I tell a joke at the beginning, because otherwise somebody else is going to say it at the end. The current status, let me finish the point about stage 3 of the energy system. Stage 3 of the energy system really will have to rely on 3 planks. Solar, probably not in Britain, advanced fission, and fusion. For the UK, that's pretty much going to be it. Right? There will be a component of wind, but that's going to peak out at probably about 30% of our electricity generating at the current size, so probably a smaller section of a bigger size. none of those three options are ready for market. We haven't done the research so that they could come into market in this in the timescale that we may even need them. So this is why the transitional technologies, current generation of nuclear, is so important to us. It gives us time to develop the new technologies, bring down the cost of solar, make sure that we can run safely and successfully with advanced fission systems and develop fusion. And the problem I'm seeing at the moment is not enough investment into these long-term research topics in order to make that happen for our market in the UK. So I'll get to fusion because it's my baby and it's what I care about most, I think. We've done some fusion. So to get fusion reactions to happen, you've got to heat the fuel, which is two kinds of hydrogen, deuterium and tritium, to about 200 million degrees. And you've got to hold the fuel at 200 million degrees some way so it doesn't touch the walls, and we do that with magnetic fields. And we've done that. And in the experiment that we have in my laboratory in the UK, which is the European experiment, JET, we regularly heat it to 200 million degrees and we get fusion reactions to happen. And in fact, we produce 60 megawatts of fusion power from that machine. 2 seconds. And the European Union has just funded us for another 5 years so that we will be producing about 20 megawatts for 6 seconds in 2017. And that will be the maximum this machine can achieve. We are building this international device called ITER in southern France. That device will do the sort of historic fusion experiment because that device is designed to get to the stage not only where fusion is happening, but where fusion is sustaining itself. So like Fermi's famous critical experiment at the University of Chicago where he pulled out the control rod and a nuclear reactor went critical, ITER, this machine in France, will actually get to the stage where the fusion reactions heat the fuel fuses, it heats itself and it keeps on burning, and all you need to do is to keep shoveling in more fuel and make it burn. And that should happen by the end of the 2020s. If that happens, nobody can say fusion is 30 years away. We've done fusion, but I'm actually exaggerating. We have not done commercial fusion. By that time, we've demonstrated scientifically that fusion is possible, and it can be sustained, can make more energy than you put in, all those things. There is a job at that point to demonstrate that you can make economic fusion at a cost that the consumer wants to pay for their energy. Now, the plan there is different in China, Korea, and European Union, and the US has no plan at all. It's often like that. The European Union has a plan to build the first electricity-producing fusion reactor, if ITER is successful, and produce electricity before 2050. The Chinese and Korean plans is to accelerate that by a decade and essentially assume that ITER is going to be successful and build the reactor before they know the success of ITER, and then put it online in the 2030s. So by 2040, I've actually produced some electricity. Now you might say, okay, 2050, it's more than 30 years away. But actually, if you look at what we have right now, we have a transitional period in energy in which we can use nuclear and carbon capture and storage to tide us over until the future emerging technologies happen. We should use that wisely. Thank you very much.
I said